Hi, this is Ryan Holger with Temperature Equipment Corporation. This Monday's webinar is on the topic of CO2-based demand-controlled ventilation, or more commonly referred to as DCV. We're going to go through this topic today, and we're going to look at it from both a code perspective, from an energy conservation perspective, as well as a how to implement perspective. So if you have any questions as the course of the webinar goes, please type them in the box, and I'll take a couple breaks throughout to try to answer them for you. Okay? All right, so the first thing to think about is that comfort in a building is more important than just temperature. It's really temperature and ventilation. And in reality, humidity plays a big portion of that as well. But for today's discussion, we're going to focus on temperature and ventilation. So how do we ventilate buildings today? The exact same way we always have ventilated a building, which is fixed ventilation. Put the outside air damper to a fixed position, lock it in, hopefully balance it at that point, and then let it ride that way for the rest of the life of the building. We don't actively control it at all. Here gives you a quick little history of ventilation rates throughout the course of time. So we'll skip all this stuff at the beginning because none of us were alive at that point. But for most of the buildings that we work in and deal with today, or that some of us are old enough to have designed, really life kind of begins after World War II in the 1950s, when we had a recommended ventilation rate of 10 CFM per person. And that pretty much carried on all the way through until the late 70s, and then we had something that many of you remember called the energy crisis. So we freaked out, we screwed all the dampers shut, or at least throttled them back, and even ASHRAE, we lowered our recommended minimum from 10 CFM per person down to 5 CFM per person. And that was pretty short-lived, because right around that time frame we started having what many people remember as the sick building syndrome, the IAQ issues. So we said, okay, well, we can't do that, so let's jack the dampers open the other way. And we went from 10 CFM per person to 5 CFM per person in the 1981 standard, up to 15 CFM per person for the 1989 standard. And that's where most of us have been designing buildings since. And then in 1999, we went to 20 CFM per person. And it stayed that way until 2004. In 2004, we switched it a little bit, and we stopped looking at CFM per person, and we started looking at CFM per person plus CFM per square foot. So one portion of the ventilation to take care of the occupant odors, and one portion to take care of off-gassing of furniture and carpets and things like that. So in a typical office building today, the ASHRAE required ventilation is typically 5 CFM per person plus 0.06 CFM per square foot. And for a typical occupant density, that corresponds to about 17 CFM per person. Pretty much the whole point of this discussion is to point out to you that pretty much since 1989 and later is really the only time we've had these higher ventilation rates. Most of the rest of the building stock you deal with on a normal basis had the 10 CFM per person rate. So as you are rehabbing these buildings and gutting them and redesigning them and all that good stuff, chances are the ventilation rates are going to be double what they were the last time this building was properly engineered. So you need more ventilation air, and you want to be able to do that in the most cost-effective way possible. So this is a typical little project here. This is a small bank designed for 20 CFM per person, which is pretty common that we do. If we had 25 people in the design, we would need 500 CFM of outside air, which makes sense. And then in actual operation, if those people weren't there, and they are seldom all there, if we're down to 5 people in the building at a given moment, we still are bringing in 500 CFM. And when there's just a one person at the bank teller, we still bring in 500 CFM, which is way more than we need. Same thing happens on zoning systems. So this zoning system here, we have a VAV style system, in this case a packaged rooftop with zone dampers throughout. In this drawing, anything that's red means it's underventilated. If it's blue, it means it's overventilated, and green would mean that it's perfect, and nothing's perfect yet because it's my slide and I didn't make it perfect yet. But chances are we might be bringing in the code required outside air at the air handler, but we have no idea if that air is actually getting to the correct space or not. And in most cases, some zones are getting too much and some zones are getting too little because we don't know if anybody's in that room at the given moment. Basically, we're not controlling it at all. So normally we put a temperature sensor in every single space, and that's what we have here, one for every VAV box. And what I'm proposing to you today, and I've been proposing to most of you for the past 10 years, is you put a temperature sensor in there and a ventilation sensor. And in this case, By ventilation sensor, I'm talking about a CO2 sensor. So I want to measure the temperature as well as the CO2 in the space. So I change those stats out to one that can do temperature and CO2, and I modulate the dampers based on that. The goal is to get the right amount of fresh air to the right place at the right time. All right, so how does all this work? The first thing you have to do is you have to understand what happens in terms of codes. ASHRAE 62.1 is the commercial ventilation standard that pretty much most of the country follows. And even if they don't follow it directly, they probably follow one of the codes that are based on it. ASHRAE 90.1 is the energy standard that most states and cities follow in one way or another. So CO2, as hopefully most people on this webinar know, is carbon dioxide. And carbon dioxide is completely different and totally unrelated to carbon monoxide. I bring this up because on a daily basis, people confuse to me CO and CO2. Today we're talking about CO2, carbon dioxide, which is a byproduct of humans breathing. CO, carbon monoxide, is a byproduct of incomplete combustion. So we're concerned about CO in parking garages and boiler rooms and things like that. CO2 is what we're looking at in terms of the occupants in the space and ventilation rates. A typical outdoor air level in this area of the country is around 450 parts per million. When I go to downtown Chicago, I can typically get levels that are 475 to 550. When I'm out in more suburban or rural areas, I'm usually around 450 when I'm measuring levels. Inside the building varies widely. They could be basically as low as the outside air level, which is about 450 parts per million, or they could be much higher, 1,500 parts per million, 2,000, 2,500. We'll talk about how dangerous each one of those levels are. For the most part, having high CO2 levels is not going to kill anybody unless you get to very, very, very extreme levels, around 35 to 40,000 parts per million. In that case, not because CO2 is harmful, it's just because you've displaced so much oxygen, there's nothing left to breathe. But small levels, even say 2,000 parts per million, that's going to be too high, but it doesn't mean it's too high because CO2 is harmful. It means it's too high because we don't have enough fresh air. So people typically exhale at about 40,000 parts per million. And as you exhale, I got a couple comments coming on that there's something with the microphone going on. Let me see if I can fix that real quick. All right, hopefully that is better and stays more consistent for you guys here. So typical humans exhale at about 40,000 parts per million, and CO2, after you breathe it out, spreads rapidly throughout a given space, just like humidity does. So I measure CO2 at the north wall or the south wall of a given room, it's probably going to be about the same. It spreads rapidly. It's not like temperature where it gets stratified vertically or it doesn't spread evenly horizontally. CO2 spreads rapidly, which is going to make it nice for us to measure in a little bit. So typical CO2 production. The reason we're looking at CO2 production is because, like I said, CO2 is not something that's particularly harmful to us. It's just a surrogate for how much fresh air we have in the space. And the reason we're looking at CO2 is because CO2 is what everybody exhales when they breathe. And if we can see how much CO2 is in the room, we can guesstimate how many people are actually in the room and adjust the ventilation rate accordingly. How much CO2 you exhale is directly related to how much breathing you're doing, which is directly related to what activity you're doing. So if you look at this chart here, on the bottom we go from 0 to 5 METs, which is metabolic units, so how much activity am I doing? And vertically, we are either looking at oxygen consumption or CO2 production, and they're directly related to each other. The more oxygen I breathe in, the more CO2 I exhale. So if I look at office work and I go down the chart, I'm basically at a MET rate of about 1.2. If I look at sleeping, I'm at a MET rate of 1. So sleeping and office work are pretty much the same thing. And since most of you are sitting at a desk right now, you know what I'm talking about. If I go to a gym and I'm doing heavy exercise, if I go all the way over here, I'm at a metabolic rate of 4. And I'm producing 4.5 to 5 times as much CO2 as if I was sleeping. Right? So what I'm doing directly relates to how much CO2 I'm producing. The CO2 in the room itself, after the amount of people coming in and out of a room fairly stabilizes itself, then the CO2 levels will stabilize themselves, assuming I have ventilation air coming in. And how much ventilation air I have coming in determines how fast it stabilizes. So on this chart, on the bottom, I go from 0 to 5 hours, in 1 hour increments. On the left side, I have CO2 levels, and each one of these curves is a different ventilation rate. So if I look at our typical ventilation rate, which is between 15 and 20 CFM per person, so I'll be either the green or the yellow line, pretty much after about a half an hour, 45 minutes, things stabilize in the room, and I got a straight line going all the way across. Right? So if I'm bringing in between 15 and 20 CFM per person, and the amount of people come into the room and doesn't really change all that much, my CO2 readings will be pretty much nuts on in about a half an hour. Right? If I have a higher ventilation rate, 30 CFM per person, it catches up faster and it stabilizes in about 15 minutes. If I have a low ventilation rate, 5 CFM per person, it takes about 2.5 to 3 hours to stabilize. So I won't bore you guys with all the math here, but this is right out of the ASHRAE 62 standard, and this basically has been in the standard before DCV was even allowed by the standard, because the ventilation rates that we have now today, based on the ASHRAE standards and the codes, are all derived from CO2 calculations back in the day. So what this basically shows you here is VO, which is the outdoor airflow rate, is equal to the CO2 generation per person divided by the difference in CO2 between outside and inside. Or another way to express it is the outdoor rate per person that we need, the CFM per person, is equal to this constant, 8,400, times the metabolic rate, the activity level, divided by the difference between inside and outside CO2 levels. So if I need 15 CFM per person and I know the outside CO2 level and I know what the activity is going on in the space, I can easily calculate what the CO2 set point inside should be. So if I do actively control CO2 based on what's going on, in that same bank job example, when I got 25 people and design airflow rate of 500 CFM of outside air, if only 5 people are there, then I only bring in 100 CFM. I don't bring 500 in. And if there's only one person there, I just bring 20 CFM per person. Excuse me, 20 CFM in because I only have one person there. All right, so I'm going to ventilate based on the actual occupancy. And I think most of you can imagine in your head, if I design it for 500 CFM, but at this given moment I'm operating it at 20 CFM, how much energy savings that correlates to, how much heating and cooling and filtering I don't need to do. On a zoning job, instead of having the red underventilated, the blue overventilated, if I'm measuring CO2 in each space and modulating my damper accordingly, everything turns green in this case because it's perfectly ventilated, also because it's my slide. The type of components you will need on one of these type of systems are going to be a CO2 sensor, and in some cases multiples. That's this guy down here on the left side of the picture. You're going to need some kind of controller on the outside air damper that can handle a CO2 sensor. That's this guy on the far right side. So that'll either be a air handler controller, a rooftop controller, and if you don't have a DDC system, it might just be the economizer itself. It might be able to take a CO2 signal in. And if you have a zoning system, then your VAV controller is going to have the ability to handle this as well. Each CO2 sensor will wire to the VAV box controller, and those will all be talking to the air handler controller. And we'll go through an example of how that works here in a minute. So why is it even important to have proper ventilation in the space? I got about 1 million studies that can point to good IAQ and productivity in spaces, CO2 and productivity in spaces. I'm going to highlight a couple of them for you real quick here. This one is Department of Energy, Lawrence Berkeley Labs, Indoor Environment in Schools. This is probably, I want to say, a 10 or 12-year-old study at this point. But they found a significant correlation between decreased performance of the students and high CO2 levels, which equals lower ventilation rates. So the higher the CO2 level, the lower the ventilation rate, and the poorer the performance of the students. The lower the CO2 level, the better the ventilation rate, and the increased performance of the students. Here's actually my favorite study of all time. Real Estate Information Systems did this study, and the number 2 complaint of tenants in a building. So they surveyed tenants after they were leaving a building because they no longer decided to renew their lease. And tenants that decided to leave, the number 2 reason they were leaving was because of ventilation issues, right? And a lot of times that's defined as too stuffy, too drafty, things like that. And number 1 and number 3, as you might guess, are I'm too hot and I'm too cold. So we're doing a really good job as an industry here. We have the top 3 complaints of tenants: too hot, too cold, and poor ventilation, all responsible for the HVAC, right? Here's US EPA. Improvements in the indoor air quality substantially increase employee morale and productivity. And then here's a really good study because it equates to the dollars, which is very difficult to do, as you guys know, correlating productivity and money. But this was a 40 building study with 3,000 people, and for every dollar they spent to improve the ventilation on these buildings, they saved $2 in employee sick time. I don't know how they measured that, because I got to assume if an employee didn't use his sick days, he used his sick days as extra vacation days. But I'm not sure how they measured it. But the better the ventilation in the space, the less sick time people had. Here's some school studies. This is from Massachusetts Technology Collaborative. This is a 5-year-old study now. 60 million Americans across this country go to school every day, and that's between staff and students. 14 million schools are considered below standard or dangerous for indoor air quality and or code compliance. And 15,000 of those 14 million actually had air that was classified as unfit to breathe. All right, so there's lots of potential in schools as well as offices and other places. But schools are a big target. And then, as you guys probably know from your own kids, between students and teachers and faculty, we spend about 85 to 90% of our time indoors between school and house. Kids don't play outside anymore like they did when we were little. Kids are inside all the time, video games and all that stuff. Everybody's inside, so we don't get the fresh air we need. And sometimes indoor pollutants can be 10 times as worse as the outdoor pollutants, and in some cases even more than that. This one's in the ASHRAE Journal 4 years ago, October 2006. Increasing outside air intake level and decreasing temperature improve the speed of the students. Increasing outside air temperature and decreasing, actually did I word this wrong? Increasing outside air temperature and increasing temperature did not improve the error rate. So if temperature is lower and outside air ventilation is higher, students are faster and have less errors. All right, so how do these guys fit into the codes? ASHRAE 62, most of you guys have heard of. A lot of the codes follow this. It feeds into the International Mechanical Code, and right now we're using International Mechanical Code 2009. The International Mechanical Code is almost identical to ASHRAE 62 for almost every topic, word by word. It's literally cut and pasted in there. There are a couple tweaks. As far as CO2 is concerned, it is absolutely identical. And in most cases, the International Mechanical Code gets adopted by local jurisdictions as their code. In other cases, like an example of City of Chicago or the state of Wisconsin, they write their own codes. But even then, they feed a lot of information off of ASHRAE 62. It is kind of the backbone of ventilation. And since 1999, we've basically allowed demand control ventilation in ASHRAE 62. It first started out in 1999 as an interpretation ruling, saying that you could use the ventilation rate procedure as an actively controlled ventilation system. In ASHRAE 62 2004, they actually wrote right into it that you can use CO2-based demand control ventilation. So we're now on year 6 of it actually being written into the code. This is what it looks like in the International Mechanical Code. I won't read it to you, but the languages between the International Mechanical Code and ASHRAE 62 are basically identical. And you can see here it actually calls out CO2 specifically as an acceptable way to do demand-controlled ventilation and reduce the air below the code required air. So ASHRAE 62.1 2007 is worded this way here now, and it's exactly the same in the International Mechanical Code 2009. It's called Dynamic Reset. And if you read through it here, it allows you to modulate the outside air rate based on indoor CO2 levels. There's other ways you can do it, but CO2 seems to be the most widely adopted way. For those that do work in the City of Chicago, it is allowed in the City of Chicago since 2003. It works a little bit different than the ASHRAE and IMC method, which we'll talk about those controls in a minute. But the way the City of Chicago does it is they allow you to have a fixed ventilation set point of 1,000 parts per million. ASHRAE and IMC have a floating ventilation set point based on what the outside air levels are. So, for example, if ASHRAE 62 says you can have 700 parts per million above the outside air level, and your outside air level is 450, then your inside set point becomes 1150. The City of Chicago ignores that, and they have a fixed rate of 1,000 parts per million for the indoor level. So it's a little more conservative than ASHRAE, but nonetheless, it does allow you to do some DCV. The state of Wisconsin 2008 code looks very similar to the IMC 2006. In fact, it does call out that you follow the IMC 2006, and they give you about 9 pages of exceptions. And this here is the section of exceptions that corresponds to CO2. So for those of you that are doing work in Wisconsin, I know it is a widely held belief in the state of Wisconsin that you can't use CO2, but that is quite not the case. It's not true. You can do CO2 systems. You just you have to be a little bit more cognizant about talking to the permit and inspector guys because they might not quite understand what it is. So I point this out here. This is the section you want to show them. Commercial section 64.0403 is what you're going to want to show your inspector or your permit guy if you're having difficulty getting them to understand that it is allowed. So if you're an engineer, which most of you on this call are, you can engineer a ventilation system that will prevent the maximum concentration of contaminants from exceeding the maximum obtainable by the outdoor air ventilation rate in accordance with IMC, blah, blah, blah. This is the exception that allows you to go ahead and do it. So basically it says if you as an engineer can basically verify and calculate that the amount of ventilation you're bringing in at a given moment is sufficient, then you can do it. And I think by pointing to ASHRAE 62 and the IMC as your design criteria, I think that's a pretty safe bet that you can point to that as an acceptable engineering method. So in addition to being allowed by codes, ASHRAE 62, IMC, City of Chicago, and even the state of Wisconsin, it's also required by some codes. So the ventilation standards now allow you to do this. The energy codes are now making you do this. All right, so this is ASHRAE 90.1 2007 that you see on the screen here. DCV is required for spaces larger than 500 square feet and with a design occupancy of ventilation greater than 40 people for every 1,000 square feet. So if I have a density of people that is 40 people per 1,000 square feet or more, and it's a fairly normal size space or larger, 500 square feet, then I have to, by law, do demand control ventilation in places that are following this as their code. So who follows 90.1 2007? Any state that's adopted that, or any state that's following the International Energy Conservation Code 2009. So that would include Illinois and Indiana. Wisconsin, not yet. They're following 2006, but they will very shortly have to bump up to 2009 to keep up with their federal requirements for staying on top of ASHRAE. But Illinois and Indiana have to do it now. Wisconsin will have to do it fairly soon. But you have to do it for these kind of spaces, and there are some exceptions to it. Like if you have an ERV, they're not going to make you do DCV also because you're getting a lot of energy savings off the ERV. Doing DCV isn't going to get you that much more, right? But if you got spaces that have more than 40 people per 1,000 square feet, you have to do DCV. So just in discussion, it's going to be places like auditoriums, cafeterias, movie theaters, retail, restaurants, those kind of places where you got a lot of people in a relatively small area. So the goal here is to have a better operating building, ventilate to the actual occupancy at a given moment instead of the assumed design occupancy, eliminate the wasteful overventilation, get a payback on this in terms of energy savings, save dollars while doing all this. So this is where the money part comes in. So when you look at this chart here, and by the way, if you guys have any questions, go ahead and type them in, and I'll take a break here in a minute to answer them. So type in the box and hit send. If I look at a given building here, at the top of this chart here is 100% of my design airflow rate. So maybe that's, say in this example, 1,000 CFM on the top of the bar here. The orange bar is my base ventilation rate. We'll say 300 CFM in this case, that I have to take care of off-gassing of carpets and furniture and things like that. A normal building, when it goes occupied, say 7 o'clock, I turn the ventilation system on, I go up to the full design outside airflow rate, I stay there all day long until, we'll say 7 p.m., then I shut it off on throughout my day. The purple is a demand control ventilation scenario. So I got my base ventilation rate, which is exactly the same. Come 7 o'clock in this case, I turn my ventilation system on. I ramp it up much slower than the normal system because I don't have everybody in the office yet. By 8:30 or so, most people seem to show up for work. By 11 o'clock, they start cutting out for lunch. That's the V you see here. This is an office building data. And then most people make it back from lunch, although not everybody. I don't know where everybody else goes, but they don't all make it back. And then around 3 o'clock, people start cutting out for the day, right? So everything between purple and green is energy savings. Green is what I would have had it designed for on a normal building. Purple is where I'm going to modulate back to because I only have so many people there at a given moment in time. That two-hump profile is what we like to call it. That's typical for an office building type environment. This bottom one here is more common in restaurant type scenarios where I got a peak for breakfast, a peak for lunch, and a peak for dinner the crowd. And for some weird reason that I don't understand, there's always a second smaller peak after each normal meal time. People come trickling in afterwards. But a restaurant will typically have those 3 peaks. An office building will have the 2 big peaks. And a school, if you look at it, will have kind of a jigsaw effect. And we'll kind of talk about that in a little bit too. So these are typical energy savings that are potentially saved with these systems. And this is based on real project data. So on the bottom, or on the left side here, is 0 to 100% of the design ventilation rate and energy associated with it. And then we have a topic for each one of them. So offices, I typically can modulate down from 100% of my normal vent rate down to about 70% on average, right? So it doesn't mean at a given moment in time I don't need 100% because I might, but sometimes I might need 50%, sometimes 70%, sometimes 80, whatever. It averages out to about 70%, meaning there's a potential savings of about 30%. Retail, it's a much more dramatic scenario. On average, I only need about 10% of the air that I had to design the building for. That's because the building's probably designed for, what do they call it, the day after Thanksgiving, the Black Friday, where everybody packs the store like crazy, right? But what happens on a Tuesday in July at 10 a.m.? Nobody's in there, but I'm still ventilating 100%. So on average, I can probably save about 90% of the CFM on a typical retail environment. Restaurants are pretty similar. I could probably save about 85% because a restaurant, kind of like retail, is designed for a specific scenario, and it's never hardly at that scenario. So a restaurant's designed for that peak day, whether it's a Sunday brunch or Saturday evening crowd or whatever it is. But then on, once again, Tuesday in the middle of the day, there's nobody there at Tuesday at, say, 2:30 in the afternoon, right? So all those times throughout the year are huge energy saving potential. And then schools, on average, a given room is only about 30% occupied on average throughout the year. That doesn't mean that 70% of the kids aren't showing up for school, although there's that problem too. What it means for the most part is that the kids are in their classroom for, say, period 1, then period 2, they leave their classroom and they go to the music room. And now there's nobody in the normal classroom. Then they go to gym. There's still nobody in their classroom. Then they come back. Then they go to lunch. Then they come back. So throughout the day, on, say, an 8-period day, they may only be in their classroom for 5 or 6 periods. And every room in the school is like that, where people are moving in and out, moving in and out. Normally, you got to design every single room for as if every student was in every room. But everybody can't be everywhere at every time. Everybody has to be somewhere and only one somewhere. So you can pretty much modulate all the rooms back when the students aren't in there, and there's a huge potential savings. These are ROIs from around the country here, and these are also off real project data. And these are probably 8 to 10 years old now at this point. And the CO2 sensors have come down a little bit more in price in that time, so the paybacks might be a little bit better, and energy costs have gone up a little bit. So, but it'll be this way or better. So real good examples are like a movie theater, right? People pack in a movie theater for 2 hours, full ventilation, then everybody leaves. You can go ahead and shut that thing down, right? So movie theaters are an excellent candidate. Retail is great. Offices are pretty good. Schools are pretty good. Anywhere where I got a lot of people in a space and those people are coming and going are the best candidates for this type of thing. This is a federal study from the Federal Energy Management Program, and you can believe government studies if you want. I'll let you guys decide that. But this was a retrofit scenario. They put 4 CO2 sensors on per floor. They did an energy model and estimated they were going to save $81,000 annually on this project, which was about $3,000 per floor. It corresponded to about 22 cents per square foot savings. Then they actually operated the building and started measuring their data, and for the first 6 months alone, they saved $133,000. Right? So they were estimating $81,000 for the whole year, and they saved $133,000 for 6 months, which is 3 to 4 times what they were actually planning on saving. And it's a pretty good chunk of change, right? These are other projects that have had these systems in there for quite some time, more than 5 years. These are names you might recognize, like the Pentagon, obviously a big name, Purdue University, and now they're pretty much everywhere. We've done at our office several hundred projects with some type of demand control ventilation, whether it's 1 sensor on a rooftop or whether it's 100 sensors on a VAV system. It can be pretty much anything. Here are some typical projects here, typical examples from this area of the country. I won't go through them all in detail, I'll just kind of highlight them real quick. This is a school district in Minnesota, proving that you can do this stuff in colder climates like most of you guys are from. Most of the folks on this call are from Chicago or Wisconsin. So Minnesota is not that different in terms of climate. But they did it for comfort and productivity. That was the reason they did it. There's an office building in Minnesota. They were doing it for energy savings, and they didn't want to hurt the tenant comfort as a process of that. They had a 3-month return on investment in this building, mostly off of heating cost savings, but a little bit on the cooling savings as well. They saved $200,000 the first year. Obviously, this is a pretty big high-rise, so pretty extreme. Indiana, Purdue University's had this system in there probably for 10-plus years at a particular facility there. They did it for energy savings and low maintenance, because when they found out that CO2 sensors no longer require the calibration that they used to back in the day, that was the difference between them doing this project and not doing it. And the payback was under 2 years. And then for those of you that ride Harleys, Harley-Davidson, Wisconsin has a system like this as well. They did it for productivity as well as comfort, and energy savings is just a side benefit. All right, so how does all this work here? I'm gonna pause for a minute and see if I have any questions typed in, okay? Okay, I don't see any questions at the moment. If you have questions, just please type them in the box, and I'll do my best to answer them as we go or at the end. All right, so when we're designing one of these systems, the first thing I want you to keep in mind is that all of the equipment gets designed exactly the same way as if I didn't have CO2. Because the worst case scenario is that everybody that this building was designed for actually shows up, and I have to ventilate for all those people. So my design day and my design equipment doesn't change. I have to still design it the same way for X amount of people in that space on a certain temperature day, and that's what I got to design it for. So all the equipment, everything stays the same, my loads stay the same. What happens, though, is in practice, when those people aren't there, and I'm deciding if they're there, whether they're breathing or not based on their CO2 exhaling, if they're not there, then I get to modulate my ventilation air back. So some people get confused, and they think that we're going to take the ventilation code air and then modulate it open from there. That's not the case. We're taking the code ventilation air and modulating it closed from there, providing less ventilation air. So I don't have to design any special equipment because I'm not going to provide any more air than I normally would have on a normal job. Just I'm going to provide less during some times of the year. There's things I have to think about, too, in addition to how many people are going to be there and how much activity level they're going to be doing. But building pressurization comes into play here. If I start modulating all these outside air dampers back, I don't want to modulate the outside air back to be less than my exhaust systems are taking out of the building, because then I'll be in a negative on the building, and then I'll be sucking doors in and things like that. So when I set up the minimums on my damper, it's going to be the minimum of what I need for my CO2 system or what I need to pressurize the building, whichever is greater. And then the other thing to think about is if you have areas of the building that have hazardous materials, those are areas you're not going to mess with. You're not going to start messing with the ventilation in a laboratory or something like that, or a dry cleaner. Leave those buildings alone. Don't touch those buildings. Just stick with the places that have people-generated off-gassing, right? So schools, retail, office buildings, things like that. Don't mess around with places that have chemicals. This is a little chart to give you an idea of which places make sense and which ones don't. In this case, A is an awesome application, C is a horrible application, and B is a maybe, depending on what they're doing in there. So good applications are libraries, music rooms, auditoriums, prison cells, sport arenas, lobbies and waiting areas, conference rooms and meeting rooms are fantastic applications. Game rooms, gymnasiums are awesome. Dancing areas, stuff like that. Places that are bad applications are pretty much places that have non-people pollutants. So dry cleaners, laundromats, kitchens, material storage, and then other places too that don't have that scenario but you don't want to mess with, like a locker room. Sure, in a locker room, all the odors are people generated, but it's not really people breathing. It's not the breathing that's causing a problem. It's all the sweaty hockey gear and all that kind of stuff, right? So locker rooms don't mess around with because you're gonna end up with odor complaints. Pet shops and pet veterinarian clinics, don't mess with those. Leave them alone. Autopsy rooms, obviously, leave them alone. Swimming pools, because of the chlorine, leave them alone. So leave those kind of places alone. And then the places in the middle are the ones with the B's, And those are ones that you just kind of have to look at. Like a dining room at a restaurant would be a great application because you got a lot of people in a small space, but it's not in practice because most of the time we use our dining room air handlers to make up the kitchen hood exhaust going out of the kitchen. So we're usually cheating in doing that, so then that makes it not a great application. But in principle, it would be. Restaurants would be great if we weren't stealing the air from the dining room to make up the kitchen. All right, so here's a chart on how to look at this here. And on the left side is percent, and that's not percent of damper travel, right? It's not 20 to 100% of damper travel. It's percent of my design ventilation rate. So the top bar there at the 100%, that's the outside air rate that I would have used for this project had I had no DCV system. Then I'm going to modulate back down from there. In this case, I'm going to modulate between 20 and 100% because I determined that 20% was my baseline that I didn't want to go below. My baseline, like I said, is either going to be the greater of what I need to pressurize the building, right, to make up my exhaust. So add up all my exhaust fans. What do they add up to? X amount of CFM. I got to bring at least X amount of CFM in. So it's either that number or it's what I believe is going to be caused by the off-gassing of furniture and carpet and things like that. Where do I get that number from? I get that number from ASHRAE. So like I said, for a typical office building, the design is now 5 CFM per person plus 0.06 CFM per square foot. So my baseline in this case becomes the 0.06 CFM per square foot, which is the 20% on this line, and I get to modulate the people part, right? So from 0 to 20 is what's taking care of my building. From 20 to 100 is taking care of my people. I'm going to modulate those back when no one's there or when less people are there. All right, we can skip the math here. You guys kind of get that. On VAV systems, it works basically the same way. You got to determine all your ventilation rates just like you would on a constant volume system. If you had no CO2, adding the CO2 doesn't change the equipment selection, right? When you control it, there's two ways to do it. The way that I'm a fan of is to put a CO2 sensor in every space. And the way I'm defining a space in a VAV project is everywhere I decide to put a VAV box. So if I believe that someone needs to have their own thermostat and VAV box in their office because they have that much different control scenario than their neighbor, well, then I also believe that that particular person needs his own CO2 sensor because if their temperature controls need to be different, their ventilation control probably needs to be different. So anytime I put a VAV box on a space in an enclosed room, I'm giving them a CO2 sensor. That's one way to do it. That's probably the more popular way to do it because it's easy, it's simple, it's clean, it's safe. You know you're going to get the right amount of fresh air to every single zone. The other way to do it is to use ASHRAE 62 equation 6.1, the critical space equation. And what you try to do there is put CO2 sensors in sample areas that you believe are going to be critical areas, and then use those critical areas to control those zones. But you really don't know that you're getting the right amount of ventilation to all the other zones that don't have sensors. It is allowed by ASHRAE to use that equation. I'm not a fan of it. I propose using a sensor in every space. So we put our base ventilation rate in. That's the whatever is higher of our exhaust needs to keep the building pressurized or to dilute building furnishing contaminants, non-occupant contaminants. And I modulate from there on up. So from 20% to 100% in this example, and once again, 100% is 100% of my design outside air CFM, not 100% of my damper travel. Depending on what's going on in the building, you may want to be a little more aggressive or a little more conservative than the ASHRAE standard. So if you're building a project to LEED standards and you're putting in all of these low VOC furnishings and paint and all that stuff, you might want to go ahead and be more aggressive with this and lower it below 20%. If you're building a regular building and it's brand new and you know all the furniture stinks and all that stuff, then you might want to be less aggressive and more conservative and use 40% as your minimum. When I'm setting these systems up on a VAV system, not only am I concerned with the outside air damper at the air handler, but I also have to control the damper at the zone level. Because it doesn't make any sense for me to open the outside air damper outside and then at the zone have my VAV damper throttle back to minimum if that's not what I need. So I got to control all the zone dampers to their CO2 level, and then if any one of those zones is not getting what it needs, then I have to report back to the air handler to bring more air in from outside. So what are typical set point levels that you might see? The CO2 set point level is going to be directly related to the design CFM per person. Right? So like I said before, that all comes out of the ASHRAE 62 equations. A typical 15 CFM per person design corresponds to a set point of about 1,100 parts per million. Right? And that's if I have a 400 parts per million outside air rate. If I have 450, like I might have in most of the areas around here, then my indoor set point becomes 1,150. Right? Basically, it's 700 parts per million above the outside air level if I want to maintain 15 CFM per person. And then if I have less or more of a rate, it goes up and down. Look at it over here on the chart. That ends up pretty much corresponding to things around 1,000 parts per million are good. Things below 800 are probably overventilated, which means I'm wasting energy because I'm bringing in 25 or 30 CFM per person. And when I get to things that are CO2 levels that are higher than 1,400 parts per million, that probably means I'm underventilating because I'm in that 5 to 10 CFM per person rate. So why do I show you this? It's pretty easy to quantify a retrofit building. If you walk in there with a handheld CO2 meter, and these things are pretty cheap. They're $500 to $1,000 to get one of these handheld CO2 meters. Pretty cheap in the grand scheme of things. You can walk into a building, take sample readings, and very quickly determine if that building is overventilated or underventilated. In either case, there's a story for CO2 control. If it's overventilated, like 600 parts per million is what you read, then the story is energy savings. If it's underventilated, like say 1,600 parts per million, then the story is poor indoor air quality. So unless you go into a building and you see between 800 and 1,200, anything outside that range is pretty much a story to help them fix something. All right, I'm going to look and see if there's any questions here. All right, no questions. So either that means that this topic is very confusing and it sucks, or it means I am an awesome presenter and I gave you everything you need to know, one or the other. So I encourage you to type a question in and challenge me on something here. All right, while I'm waiting for questions, we'll keep chucking along here. There's three major ways to control based on CO2. The first is set point control, which is relay control, and it is the older, simpler way to do it. We don't use this very much anymore unless we're putting it on a retrofit on, say, constant volume rooftop units. A lot of times those economizers have the ability to take an override signal. It's basically on-off control, right? So the CO2 level gets to a certain set point, say 1,200 parts per million. We click on the relay, which takes the damper from minimum base ventilation rate back up to our normal design ventilation rate. Then we get below our set point, we close it again, and then open, close, open, close, open, close. So we're just popping between 2 points all day long. It's a pretty crude way to do it, but it's easy to retrofit on an existing rooftop unit. A much better way to control it would be with a proportional signal. So if you look on the bottom of this chart, I got differential between inside and outside levels of 100 to 700 on this chart, which typically corresponds to an inside CO2 of, say, 500 to 1,100 parts per million. And then on the left here, I have on the top line, I have my design ventilation rate, which is my damper or my economizer's fixed ventilation position. And then below that on the bottom line, I have my new minimum ventilation rate, my base ventilation rate, if you will, that I'm going to be allowed to throttle down to because I have CO2 control. So if I was up at 1,100 parts per million, my damper would be open to its design ventilation rate up at the top here. And as I lower my CO2 in the space, because I'm bringing enough outside air in or because people are leaving the space, then I'm allowed to throttle my damper back below the design code ventilation air. And in this case, all the way down to 500 parts per million to my new rate. At any point in between there. So I could pick any indoor rate, any indoor CO2 rate, and correspond that to a damper position. That would be proportional control. And then one step above that would be a PID loop, proportional, integral, and derivative. I'm just showing PI loop here because in HVAC, we very seldom use the derivative. We almost zero it out in every case. So a PID loop for HVAC is really a PI loop. It just doesn't sound as cool because we like three-letter acronyms in the HVAC world. So a PID loop. So this red line is my proportional control, which is the same as this chart over here that we just showed you a minute ago. When I do proportional integral control, the integral is basically I'm trying to predict how fast I'm getting to set point. So proportional control is I'm at this certain level, I need this certain damper position. Proportional integral means I'm at this level, I need this damper position, but how fast am I changing? How close am I getting to my next level? What's my rate of change? Let me speed up or slow down my calculations based on that. So I get more of a curve pattern that gets me closer to my reality here. It's just a better way to do it. Where do I put the CO2 sensors? That is a very common question. And like I said, the first thing is I like to put a CO2 sensor everywhere that I need to have control. So if I decided that it was a good idea to put a temperature sensor or a thermostat in a particular space, that's probably the same space I want to put a CO2 sensor in. Right? I typically do not want to put these things in the return duct. The return duct is going to give me an average of everything that's going on in all of my rooms. Well, if I have individual offices and then I got an open floor plan cubicle area and then I got a conference room and they're all in the same air handler, putting one sensor in the duct doesn't do me any good because it's always going to say I'm nuts on, even though everybody just left their desk and piled into the conference room. Well, the system's delivering enough fresh air, which means the correct amount of CO2, but it's going to all these other zones that nobody's in, and it really needs to be directed over to the conference room where everybody just walked over to. So putting it in the return duct is a horrible way to control it on an office building environment. Return ducts make sense only in large open areas like a gymnasium where all the air is kind of being pulled together anyway. So a gymnasium or a movie theater or something like that where it's one piece of equipment for one large room, that makes sense. Putting it in an area that has zone dampers or even has constant volume but has cubicle walls, partition walls between the private offices and the cubicles, for those you got to put it in the space. When you put it in the space, you typically mount it in the places that you mount a thermostat. So I want to stay away from windows and doors because windows and doors tend to have a solar effect on the thermostat reading. Well, for the CO2 sensor, it tends to be places that drafts are likely to happen. So I don't want to have it there because then I'll get a false reading. I don't want to put it places that people are going to hang out, like the water cooler or the copy machine or anything like that. And I want to have it in the breathing zone, which typically means between 4 and 6 feet high for most spaces. And then if I'm having one large area, say like an open floor plan office area, one CO2 sensor can handle 5,000 square feet of open floor plan space. So if I have 10,000 square feet, I'd put 2 sensors in. If I got 7,000 square feet, I'd put 2 sensors in. If I have 4,000 square feet, I could put 1 sensor in. All right, so I could put 1 in that office area, even though it might be served by 2 or 3 VAV boxes. And then for the office, the private offices in the conference room, I would put their own sensors on there. That just kind of summarizes it for you, gives you an idea of all the things I just said there a minute ago. All right, most economizers on rooftops can accept a CO2 signal. All modern, new rooftop equipment can handle it, and most older existing economizers can handle it as well. It may not be the most optimal control sequence that's built into it, but it can still do it, and it can still save some good energy. And pretty much every BAS system, every new BAS system can handle it, and most existing ones can. I know in terms of Carrier, we can handle it back to stuff that's probably late 90s. We started putting IAQ control into the building automation systems. And obviously anything you wrote custom, you can do whatever you want with. All right. If you don't have an economizer on the system already, you're obviously going to have to add that outside air damper control. Which is a good thing in general. If you have an old rooftop that has a fixed position damper on it for ventilation and no economizer, putting the economizer in, that right there is a huge energy saving story. And then putting it in and modulating it based on CO2, that'll save you quite a bit of energy. All right, so is this a new concept? Absolutely not. This stuff is old, well, old SHIT, right? It's been around forever. This is the 1916 Engineer's Handbook, which hopefully none of you guys were around when that was written, or maybe you got some copies from the 60s. But even since 1916, it said the CO2 in the space should not exceed 8 or 10 parts in 10,000. But what's 10 parts in 10,000? That's 1,000 parts per million. That's a pretty common number we're going to hear over and over again. So 1916, 1,000 parts per million. 1929, the New York Building Code dictated that CO2 levels should not be greater than 1 part in 1,000, which is 1,000 parts per million also. And that number carried through until it made its way into the ASHRAE standards in 1989, where we dictated DCV should have a 1,000 parts per million rate. And then in 1999, we switched it over to a differential between outside and inside. So we got rid of the 1,000 parts per million, and then now we have a differential between inside and outside. So for a typical office building at a 15 CFM per person rate, the differential would have been 700 parts per million between inside and outside. So this stuff's been around for a while. It was just in the 90s that we started actually spelling out that you can use it to actively control the ventilation and cut back from the code required air. Why are these systems more popular now? I started talking to people about these systems back in 2000. And at that point in time, pretty much no one wanted to hear what I had to say. They believed me that it saved energy, but they were, scared as hell as cutting back the ventilation rate from the code required minimum. Well, now all the codes have changed, and they all allow you to do this now. They allow you to cut back from the code required ventilation rate to a new base ventilation rate and modulate in between those two based on CO2. So in 2000, nobody wanted to hear what I had to say. By 2006, it became a pretty popular topic that everybody wanted to talk to me about. And unfortunately, I don't sell CO2 sensors anymore. But when I used to, it would have been much more fun if people accepted it. Energy costs have increased and probably will continue to increase for quite some time. Energy codes play a big factor, like we said. Now, some cases, the energy code actually spells out that you have to do DCV, and you don't have a choice if it's a densely occupied space. LEED buildings have played a part in this as well. Not only are you trying to save energy on those buildings, but you can also be awarded a LEED point for outside air delivery monitoring. And the way to do that for densely occupied spaces is to use CO2 sensors. And then for non-dense spaces, you do an outside air CFM station. But for dense spaces like auditoriums, theaters, those kind of places like we talked about, those places you have to use CO2 sensors if you want to get that point. And then the two real big things are the cost of the sensors and the sensor reliability, which I'll show you here now. This was a sample cost here, 1992, $1,500 per point. And things have gone down considerably since then. 2003, $400 per point. And things are pretty much level since that point. It hasn't really changed much. But the cost of these things, you can see, has come down 3 or 4 times, which is a big difference. The other thing is the reliability. You used to have to calibrate CO2 sensors every 2 years. That would not be a fun activity. If you had 100 sensors and you had to go around and calibrate all of them, not so fun. Now these things are pretty much designed with, depending on the manufacturer, a 10 or 15-year design life. And most of them have an automatic calibration routine built into them. This one's called automatic baseline calibration, ABC logic. And what it basically says is if I have an unoccupied period at nighttime when nobody's in my space, and I got to do this at least once every 2 weeks or so, but usually every night in the building it happens, I'm able to recalibrate all my sensors to match the outdoor air base ventilation rate. Right? So what that looks like here, this is 3 sensors, red, yellow, and whatever color that is, purple, over the course of 4 or 5 days. They started out apart from each other, they drifted apart, and then they end up recalibrating themselves to basically read the same 425 parts per million. Same 3 sensors over 2 weeks, and they pretty much stay very close to each other within 25 or 50 parts per million all the time. And those same 3 sensors over 3 years, with a known concentration of CO2, 980 parts per million, blowing directly on them, for 3 years, they pretty much stayed online. Right? So these things self-calibrate themselves. You can't go in and calibrate them anymore. Some of these manufacturers have actually removed the calibration button because they don't want people to calibrate them anymore, because you actually do more harm than good when you falsely calibrate them, when you incorrectly calibrate them. So if you have one of these types of sensors from one of these manufacturers like Telair or Carrier or Honeywell, what actually ends up happening is if you have to calibrate it because something's wrong with it and drift it out, you actually return it back to the manufacturer and get a new one under warranty. And that doesn't happen very often. Looks like someone did type in a question here, Dan, asking if we can discuss how room CO2 sensors in a VAV system control both the VAV box and the outside air damper on the rooftop unit. Yeah, that's a fantastic question, Dan. I was actually going to show you guys a video of how that worked. I could not do that because I can't play videos through the webinar service. So I'll just describe it verbally real quick, and then we'll move on with the last few slides. So on a VAV system, what actually happens is the CO2 sensor wires to the VAV box. This is going to require a DDC style of VAV box controller. So the CO2 sensor wires to the VAV box. As I am approaching my CO2 set point, I start modulating my VAV damper open more to provide more air in there. And right now I've done absolutely nothing with the outside air damper on the air handler. I try to open up my ventilation damper, or my damper on my VAV box to get more ventilation air and steal that air out of the system. However, if I've opened up that damper as far as I can and my CO2 level has not come down, then that box can report back to the air handler that it needs more fresh air, and that damper on the air handler will start modulating open. So basically, each VAV box gets controlled to its own CO2 sensor to modulate between its minimum and maximum CFM set points. And the main air handler itself is only looking at the worst out of all those boxes. So if I got 25 VAV boxes on one air handler, I look at all 25 of those with the DDC system, figure out who's the worst, and I control my outside air damper to him. Now, usually at this point, someone asks me, well, am I going to overcool by opening up those zone dampers on the VAV boxes for CO2? The answer is yes, and the answer is no. The first thing you have to remember is I'm not going to be modulating this damper open more than a normal job. I'm actually going to be modulating it down from a normal job. So if my normal job was 300 CFM minimum, maybe on this job with CO2 sensors, I put 100 CFM minimum on that VAV box, and I modulate it between 100 and 300. And then I can still go higher to that for temperature reasons. So I'm not going to bring in more air than I would have on a normal job. I'm going to bring in less when nobody's there. When everybody's there, I bring in the normal design amount of airflow. If that normal design amount of airflow would have caused me to overcool the space, then yes, I'll have an overcooling issue, and I can either kick on the reheat, or I can just leave it be as is, depending on what I would have done on my normal job. The point is I'm not going to modulate it more than a regular job. I'm going to modulate up to a regular non-DCV job. And the same thing is true on the air handler on the outside air damper. I'm not going to say, oh, my normal job said I had to have 30% outside air. I'm going to modulate it from 30 to 100% damper position. No, I'm not going to do that. I'm going to modulate it from 30% down. So 30% is where I'm going to be at if I need to bring in more air for CO2 control. And when there's less people in the space and less breathing, I'm going to throttle back from the 30% down to 20, 15, 20, whatever it needs to be. Right? So I'm going to modulate down, not up. I'm never going to bring in more than the code required outside air. I'm never going to bring in more than the code required ventilation rate to the VAV zone. So hopefully that makes sense. So with that being said, I don't see any other questions at the moment. We'll finish these last couple slides up and then we'll look at questions again. The goal here is to ventilate to actual occupancy instead of the assumed design occupancy, eliminate the wasteful overventilation to save energy, but still make sure I provide enough ventilation air to comply with all the applicable codes. And then in some cases, I might have to do this because the codes are requiring me to do it, depending on the type of space I have. The return on investment is very, 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 very attractive. We do a lot of energy-saving technologies here at TEC, ERVs, variable refrigerant flow, chill beams, all this stuff. I can't think of too many things that can save as much energy for as little investment as a CO2 sensor. Maybe a programmable thermostat and an economizer. Those are the first two things you put on. When you're ready for your next third technology to implement, CO2 is probably the next thing you should think about. So programmable stats, economizers, and CO2 are the order of fast payback of things you can do real simply. I do want to point out that there are other ways to do demand ventilation type systems. CO2 is my personal favorite, and it's widely accepted, and it's dictated in ASHRAE and the International Mechanical Code that it's allowed. But there are other ways to think about doing it or think about doing things similar. So this last slide just kind of shows some of those. There are other ways to have occupancy sensors, and many of you have seen these in buildings. They're either motion sensors or thermal sensors or a combination of the two. Combination is best because it'll have the least amount of false readings. And typically you see it to turn on lights in a space. You can also use it to relax the HVAC set points. So if nobody's in the space and moving, I don't need 70 degrees. Maybe I can set back to 67 or something like that, or set up in the cooling season. And also take my ventilation rate down from the maximum that I would have had for design down to some minimum base ventilation rate for the off-gassing of the furnishings only. Sometimes you can build that into a thermostat. Like this here is an LG PTAC thermostat that has one of those sensors built into it that can relax those set points. Another way to do it is with key cards. This is very popular in the hotel industry. You might have seen this if you've been in places out of the country. It's pretty popular in places that have high electricity costs. When you walk in the room, there's a little slot. You put your room card in the slot. You put your card in the slot. The HVAC and the lights work. You take your card out of the slot because you're leaving the room. It kills the HVAC and it kills the lights. Maybe it doesn't kill the HVAC, but at least it puts it back into a setback mode, right? So no key in the slot, no HVAC for you. On larger buildings, especially office buildings, you can have those key fobs that you use to get in and out of the building. But when you leave your office and then leave the building and swipe out, but you forgot to turn your lights off, well, when you swipe out, let's go ahead and automatically turn your lights off for you. And we also know you're not there, so let's go ahead and cut your ventilation rate back and let's relax your HVAC set points to save some energy. And then the last, well, there are a couple more ways here. I'll show you two. There's light-activated thermostats that have a photo cell on top of them. When the lights are on, the stat goes to occupied set points. When the lights are off, the stat goes to unoccupied set points. And also doesn't bring in any ventilation air. So if it's unoccupied, no vent air from outside. If it is occupied, we go to minimum vent position. And then the last way to do this kind of thing, if you have buildings that have operable windows, which is fantastic. If you want to have natural ventilation, awesome. But if you got natural ventilation going on and your window's open, why am I also giving you mechanical ventilation? No, I'm not. So you put those little sensors on the window. They look like the security sensors you might have at your house. The window's open, the sensor opens, tells you you don't get any HVAC, any ventilation, right? Windows open, no HVAC. Windows closed, yes HVAC. It's that simple. Here's a case study. This one is a ComEd case study. This one is a hotel application, 352 guest rooms, or excuse me, 311 guest rooms. They added a building automation system, including occupancy sensors, right? So when the doors open and they detect motion in the room, the HVAC goes occupied. So what this happened here is a total project cost of $137,000. They saved 465,000 kilowatt hours per year. ComEd gave them $32,000 of rebates to help do this. And in this case, it would have been a payback of 3 years. With ComEd's help, it made it a payback of 18 months. For those of you who don't know, ComEd has ComEd, as well as the gas utilities, Nicor, Peoples, and North Shore, all have rebate programs that are available. None of them spell out CO2 DCV, but all four of those utilities in our area here have a compliance path that can be custom. So if you can show an energy improvement by something, you're able to do this. So a CO2 sensor saves a lot of gas and a lot of electricity. You can actually double dip, and you can get a gas rebate from Nicor, an electricity rebate from ComEd, and double dip on that to help pay your project back. We do have software tools available to help you calculate energy savings. This one is a Carrier software tool. It's actually run by Telair, which is the sensor manufacturer for Carrier. There's another one from Honeywell that we use quite a bit as well. The one from Carrier is pretty nice because it gets pretty detailed, and you can model things pretty detailed. The Honeywell one's nice because it not only looks at CO2 but also gives you payback figures for thermostats, programmable thermostats, and economizers as well. So we use both of those depending on what the project's like. In both cases, you can put a simple project in there and get a very quick energy analysis in about 5 minutes. So is it an energy modeling software? No. Is it a quick analysis tool to decide if a project might make sense or not? Absolutely. That's what these tools are for. If you're doing a lead job and you do the full energy analysis, that's great, but that's a whole other tool and a whole lot more time. This is the quick and dirty stuff to give you a quick report on what to do. So with that, looks like I went 5 minutes over. I'll look and see if we have any final questions. And if we do, I'll try to answer them. If you don't have any questions or you haven't typed them in, you're more than welcome to call me about them or send me an email. My contact info should be in the bottom right there, or excuse me, bottom left of the screen, 708-670-6383, or ryan.hoger@tecmungo.com. I don't see any other questions being typed in, so I'll assume that I did an awesome job and everything was perfect. If that's not the case, give me a call and let me know what you want to learn more about. With that being said, I thank you guys for calling in. We'll have another webinar on Monday next week. And if you're not on my email currently, getting all of the training information every week, let me know and I'll send you a list of classes that are both webinar as well as classroom classes for both the Chicago area as well as Wisconsin and Indiana and other neighboring areas. Thank you very much for your time, and we appreciate it.